In this video, we're going to keep proving the MGF of standard normal distribution. So yeah, let's get started. So what we're going to do is get MGF of x, which follows normal distribution with the mean of mu and standard deviation of sigma, like this. So we're going to get MGF of normal distribution first and put 0 and 1 each into the mu and sigma so that we can get standard normal distribution and its MGF. So let's get started with MGF of normal distribution. So we suppose that x follows normal distribution, so it'll be MGF of x, the variable x. So the notation goes like this, and it's going to be expectation of tx, like this. Oh, let me write it here. Expectation of tx, and when x is, because we know that x follows normal distribution, which means x is a continuous variable. So by the definition of expectation, it would be something like this. This would be the variable in the expectation, and it was the definition of MGF, which we already saw many times through the previous videos. And we know that it's the PDF, right? And we know it follows normal distribution, so we're going to put the PDF of normal distribution in this place. So it would be something like this. If you know the PDF of normal distribution, it looks like this. So this is the PDF of normal distribution, which follows the mean of mu and standard deviation of sigma. So it looks like this. So the basic idea is that we cannot calculate this because there's a variable x here, and we wanna put these parts together and make x to get subject here. Like it sounds a little tricky right now, only on words, but it do go more more visual when you actually see the process. So finally, we're going to use the concept that the integral of the whole range of PDF is 1. So we're going to use that to get the MGF of the normal distribution. It sounds a little tricky right now, so let's just start doing it. So as I said, this is the case that we need to deal with. Because, okay, just to put one more, if it's not here, if this one not here like this, then it's the summation of PDF, the whole PDF for whole range. So it's going to be 1, right? Because like we saw many times that PDF equals 1, because we did the summation for the whole probability of each x. So that is the same concept here. But we know that there's a uninvited guest here, so we want to do some work with that to make it easier for us to calculate. So here's what I'm going to do. We put this out like here and put it back to integrate with this. So it's going to be, so this part, we can write it like this to integrate with this part. So it's the same process. So it's going to be, oh, it's a little not clear to see. So it's going to be like this, right? And we calculate this part. Is going to be x squared minus 2 times mu times x plus m squared. I mean mu squared like this. It's going to be like this. So let's continue our work. Here's x and here's x2. So we want to integrate this part to make another form of this like this. I mean the perfect square form like this. Okay, so let's keep doing. So it'll be the same here, and we put this part into this part together. So it's going to be the similar process. So let's see. So we gotta put minus to take it into here because here's minus. So minus 2tx and minus 2 mu times x plus mu squared and tx like this. So it's getting more complex here. So let's just put this part and take a look in more detail. Like this, only this part. Oh, actually it's divided by 2 times sigma squared, right? So let's just take a look only for this part. So it's going to be squared and minus x squared, and we can see that there's minus 2 in common here, and also x, so we're going to put it out. So minus 2 sigma squared times t minus mu times x, and we want to make a perfect square by this. So we want to make the perfect square artificially. So it would be minus mu, the square of this, to make perfect square in this part. And because we artificially intentionally put this part which was not there before, so we gotta subtract it to make it this part into 0. Okay, so this was that, and we had mu squared here, so it would be mu squared like this. So let's keep doing. It's going to be 2 times sigma squared, and this part is going to be a perfect square form. So x minus sigma squared t minus mu, and is square, right? This part is going to be like this, and we put minus here. Let's just take it out. Just minus here. So minus is going to be plus, and it's going to be negative. So sigma squared times t minus mu, and is square, minus mu squared. Okay, so finally it's going to be 2 parts like this. X minus, let's just take it without without bracket. It's going to be sigma squared times t plus mu, and is squared, and plus 2 times sigma square and sigma square times t minus mu any square minus mu square, like this. So this was the part we decided to take a look in more detail. So let's put it back to our original form. To make it clear, is this part, right? So let's put it back. It's not going to be same like only this part. We took it more like to see more in detail. And minus infinite plus infinite, it would be like this and this part. So it's going to be minus the square x minus sigma square times t minus plus mu, and it's squared, and then because it's plus and it's going to be like times here, I mean multiplication, so it's going to be like sigma square times minus mu square and mu square, like this. And we know that this part, there's no x, which means it's going to be a constant in this form, so we can take it out. So let's take it out. So it's going to be like out of this integral form, times square and sigma square times t minus mu and its square minus mu square, and other parts will go the same, like this and like this, x minus sigma square times minus plus mu square dx, like this. And you can see that this part is actually a PDF of a distribution which has the mean of minus plus sigma squared times, this is the mean of this distribution and standard deviation of sigma. Because like here, when we go up, here it's a little dirty here, I apologize, but we talked about it, this, and this was the PDF of a distribution which follows the mean of mu and standard deviation of sigma. So this part there is the mean of this distribution, and this part is the standard deviation of this distribution. And we come back to our new form, and we see that like let's write it in a more like easier form to see. Minus is going to be like this, and 2 times sigma squared. So we can tell that this part would be the mean of this distribution, and this part is the standard deviation of this distribution. And anyway, it's a normal distribution, so we can tell that we integrate like did the summation for all the parts, like whole range, so it goes 1. So this part is going to be just 1, so not gonna affect the result of the calculation. So if you write it again, it's going to be exponential of 2 times sigma square times t minus mu and square minus mu square times 1. So it's not going to be there. So looking back, it was the moment generating function of x. So it looks like this, minus mu square minus mu square. So this is the MGF of normal distribution.